tolerances, but you don't have to get them going away to a manufacturer and say, can you just build me one of these, and go through all that design process. You can buy the nodes ready in a little box, and so long as that's got the right sort of sensors that you want, you can program that and use that one to sort of work with. And there's the sort of info there on minimum and maximum values and how accurate the things are. Which might be of interest though, is how good is this at communicating? Like how far can it send its data? That Bluetooth, sorry, that little flick button, that thing can communicate about 20 metres, so you get it. If I walked outside, walked into the main area and clicked it, the phone probably wouldn't sort of go off to it. This one's got a bit bigger batteries on it. That can communicate about 50 metres to sort of send it. It's not going to send stuff to my home from here, but it's enough to be able to send to the central node. Now these nodes, how far can they communicate? Around about 30 metres for it, depends on whether or not you attach another antenna. How much power do they use? How much power? Basically, what size battery do they need? This only needs a tiny little watch battery. That uses the AA batteries, 2 of those. This uses a couple of AA batteries, I think. Somewhere on it there's the power. Oh, there it is, yeah. The input power, it basically uses 2 1.5 batteries for it. A bit on the power consumption. Now, a lot of these figures and concepts we'll need to come back to when we look at our operating systems, because a lot of the problem with these devices is that they draw power all the time. Just like, you know, again with your phone, say you've got your phone, you know you can put it in sleep mode. Why does the screen go off after 10 seconds? If it was on all day, the battery would go flat. Yeah? Why do you want to turn the Wi-Fi off if you're not using it necessarily? Because again, it draws power for the battery. So all these sensors, all these actuators, all sort of draw power. And so what you want to do is minimise that sort of current draw to increase its life. And we're looking at all sorts of techniques about doing that. One of which is to use the right communication protocol. Just as an analogy, I finish I do 2 lectures on a Monday morning. I do the enterprise programming and I do this one. And I can tell you when I get back to my office at 1 o'clock, I flop out and go, oh, that's because I'm talking loudly. So that you at the back can hear me. If someone was talking to you, I can talk in a whisper or more normal voice to people at the front. You at the back can't hear it, but you know, hopefully, that when you start to talk in a loud voice or shout, it uses up a lot of energy to do it. So that act of me communicating over a longer distance takes more energy out of myself. I'm just talking in a low voice. You can talk, you can do that work at a lower thing, at a lower pitch, if you like, and use up less energy. And it's the same thing, really, for these communications. The further they've got to send it, the more power it takes. So we'll have a look at that next week, about how you might sort of work with different approaches to it. Now there's a bit more in here about how long the power lasts and the like, but I'm going to leave it there for this week. If you can just finish off reading this, and I'll pick up from about this point next week. Thank you. Sorry to hold you up. Can someone bring the register down, please? Yeah.
Thinking about the node, I feel like that's something.
You probably will do, yeah. Can I just pack up and then we'll talk on our way across, because there's generally somebody waiting to come in.